Adrian Suciu from Analog Devices Incorporation, and I will present the measurements on using GNU Radio to do signal acquisition and analysis with Scopy.
Thanks. So, my name is Adrian. I've been working with analog devices for the past 4 years. My presentation will be on how to do signal acquisition analysis and with Scopy and how we use GNU Radio to do that. Before we begin, I'd like to talk a little bit about Analog Devices Active Learning Program. So this program aims to inspire students understand real-world analog signals, and it tries to bring technology to the classroom. So besides free courseware, labs, books, tutorials, we also have a few entry-level hardware platforms. So there's the ADAM 1000, which is a software-defined measurement platform. We have the ADAM 2000, the board we're going to talk about today, and also the ADAM Pluto, which I know you know, which is an SDR. So the ADAM 2000, or just short, it's the M2K, is a USB-powered multifunction instrument. It is based on the same infrastructure as the Pluto, and it has a Zinc SoC that is running embedded Linux, but the analog front end is different, and it has an AD9963 chip. Also, like the Pluto, it has several connectivity options. It makes use of the USB OTG, the USB cable to connect to the PC, or you can use the OTG capabilities along with the Linux drivers that are, part of the system to connect a memory stick, a Wi-Fi dongle, an Ethernet dongle. So you have multiple connectivity options with the M2K. So the specs of the board are a 2-channel 100 megasamples per second ADC, 2-channel 150 megasamples per second DAC, positive and negative plus minus 5 volt power supply, and 16 digital input-output channels that are capable of buffered operation at 100 megasamples per second. The hardware and firmware is open source, and you can find it and hack it at the links in the presentation. So the software that we develop for the M2K is a touch-friendly, kind of modern-looking Qt-based application. It is cross-platform and runs on Windows, Linux, and Mac OS, and it has several virtual instruments that we implemented. So there's the oscilloscope, there's the signal generator, the voltmeter, the power supply, the spectrum analyzer, the network analyzer, the logic analyzer, and the pattern generator. And most of the signal processing and acquisition on the analog part of it is done using GNU Radio. This software is also open source, and you can clone it. Maybe you can help us with it, and the link is in the presentation. So I prepared a small demo, like a teaching demo on how R2R ladder DAC works. So here we have, I have this circuit built here on a breadboard, and it kind of shows a little bit about the digital and analog capabilities of this instrument. So here we have the R2R ladder DAC, which is connected to the digital side of things, and I feed it digital signal from the pattern generator, and then I measure the signal here, the analog signal here, and see how it looks. And this is the application. So right now, this is the signal that the digital signal that we feed it in. It's a binary counter signal at 1 megahertz. And if we look at the oscilloscope, you can see that the output does not look that well. It's kind of, we have like small artifacts here. And this is because when we did the setup, we didn't really pay attention to what the op-amp data sheet said. And we didn't power it properly. But if we go to the power supply and we set in more negative voltage so it doesn't clip the lower rail, you can see that the signal looks nice. So it is just a simple example of how you can use the ADAM 2000 as a teaching instrument for students or people who are new to analog electronics. So why did we choose GNU Radio? It provides a lot of signal processing blocks that were useful for our application. The library is geared towards performance, so it should run on most PC hosts. We want to run it on Raspberry Pi. We also want to run it maybe in the future on Android-based platforms. And it also, a big deal for us was that it already had a QWT-based visualization block, so we could hack those, and we could change those to better fit our application. So in order to better understand how this system works, we should take a look at the analog signal chain. The M2K is an embedded Linux host which uses the IAO subsystem. IAO stands for Industrial Input Output. It uses the IAO subsystem to manage its inputs and outputs. The libiao abstracts this, is a system library, and it abstracts these low-level details of the subsystem. IAOD is IAOD, which is IAO daemon, is an application that runs on the M2K board, which provides remote connectivity to the board via USB, IP, or even a serial link. On the other end, we use again IAO and libiao, but along with this, we use the GR-IAO out-of-tree module to communicate with libiao, and eventually we use GNU Radio and QWT to plot the signals into Scopy. So how do we use GNU Radio? We created this IO manager class, which is basically a multiplexer between the input-output of the hardware and the instruments. So, for example, you can't have instruments that use the same resources running at the same time. So, for example, you have the oscilloscope, which uses the ADC, and the spectrum analyzer also uses the ADC, but the settings between them might be conflicting, so you can only run one of them at one time. So we created this IO manager class that handles this. And this is like a simplification of what the IO class looks like. But as you can see, we kind of abuse the copy blocks. So in order to have this multiplexation behavior, we kind of abuse the copy blocks to turn on and turn off certain parts of the application, so we don't get glitches on other instruments. Even so, sometimes this approach does not work entirely, and what we noticed is that GNU Radio does not handle flow reconfiguration, especially runtime flow reconfiguration that well. So in order to help with this IO manager class basically saves all the created data paths, all the created paths in the flow, and if we have to destroy, let's say, this block here, the IO manager just kind of remembers everything that is in front of that block and recursively deletes everything at runtime. So I'm going to talk about the instruments a little bit. The oscilloscope, like I said, is a 2-channel 100 megasamples per second ADC, which has a plus minus 20 volt input range and is capable of triggered operation. So some of the features that we have that use GNU Radio are the autoset feature, the AC coupling, reference channels, and math channels. A few words about acquisition and triggering. So in order to have, so the M2K precisely controls the trigger position. We know exactly at which timestamp the triggering occurs, and the M2K has a trigger logic core to handle this operation. However, GNU Radio does not handle the concept of triggering that well, and we used, inside the GR-IAO, we used the stream tags, which basically say the GR-IAO calls the IO buffer refill, which gets data from the M2K. And whenever this operation occurs, it also puts in a stream tag. So having the information from the trigger logic core, as well as having the buffer start tag, we can precisely draw the triggered waveform on the screen, and you can see exactly at which sample the trigger occurred. The autoset feature is kind of a user-friendly feature for people who are not that accustomed to an analog oscilloscope, to an oscilloscope. So what it does for you is help you set the time base, the volt per division, and trigger settings to if you don't know how to handle all the knobs. And it uses the GNU Radio FFT block to find the highest amplitude node tone of the signal. And when a suitable tone is found, it sets the time base based on the frequency of the tone. Once the tone is found, it looks at the raw data and it analyzes the positive and negative peaks in order to set the volts per division and trigger settings. AC coupling is also a feature that we have. So we don't have physical AC coupling, we have digital AC coupling, and what this means is that we have a digital low-pass filter that we implemented in order to get the signal that we want to filter out, and we subtract the two signals in order to get the filter result. However, there's a limitation as opposed to physical AC coupling. The original signal needs to be within the hardware input range. Also, another feature that we have is the reference waveform. To implement this, so what the reference waveform feature does is that it allows you to save waveforms and later reload the waveform. So, for example, if you have a waveform that you know is perfect and you're analyzing a circuit and you're trying to reproduce it, you can load it up on the plot and then see how the actual waveform looks like compared to the reference waveform. And in order to do this, we abuse the vector sink and the vector source blocks a little bit. We got the data from the hardware, and we encoded it in a read-friendly CSV format. And eventually, when we want to plot it on the screen, we use the vector source we decode the data from the CSV format, and we use the vector source to display it back on the screen. The math channels are also a pretty interesting part of the oscilloscope. It uses the IAO math block from our GRIAO out of 3 module. And what it basically does, it allows our software to compute the result of a mathematical equation from a string, and everything is done at runtime. So it was implemented using a Flex and Bison parser, which creates a GNU Radio hierarchical block dynamically, and it can take the acquired signal as an input, or it can even take multiple inputs if you want to do functions of multiple inputs. So I have a small example here on how the IAO math block works. So in this example, we compute sine of x plus sine of 3 times x, and then everything is divided by 3. So in order to do this, the IAO math block parses the string, and it creates this sine block, computes it. Then it takes the x, it multiplies it by 3 here, then applies sine on top of that, and then everything gets divided by this constant source by 3, and eventually everything gets added up together, and we get the signal that we want at runtime based on a string. So this can also be useful again for teaching purposes. Okay. The next instrument that we have is the signal generator, also called the arbitrary waveform generator. It can be used to generate basic signal types such as a sine wave, triangular wave, square wave, sawtooth, and it is all provided by the SIG source block from GNU Radio. It also supports file input, so you can load in binary data, WAV files, CSV files, as well as math formats from MATLAB. The cool thing about it is that it can also generate signals from math functions using the IO math block I mentioned before. And on top of this, on top of any of these signals, you can add noise if you want to have like a noisy source signal to see how your circuit behaves in, let's say, noisy environments. The next slide is a spectrum analyzer. This instrument is pretty straightforward. It uses the FFT block to compute the spectrum. We have a bunch of windows that we can apply on top of the signal, and it has averaging and marker functionality. This next instrument that also uses GNU Radio is the network analyzer. This network analyzer computes the frequency and phase response of a circuit. So in order to do this, it sweeps through the frequencies that the user selected using the arbitrary waveform generator, and for each frequency, it computes the frequency and phase response, and it plots it on the screen. So this has countless applications. Also, we have both the Nyquist and the Nichols plot. So this has countless applications, and we actually have a new update on the network analyzer, and it has a few more features I can show off later if you want. This is the flow graph that we used for the network analyzer. I'm not going to go too much into detail about this, but just wanted to show you that GNU Radio helped us a lot to implement this instrument. The logic instruments are not really GNU Radio related, but I might as well mention them here. So the logic instruments support the 16-channel digital channels, which have a buffered operation, like I said, at 100 megasamples per second. So we implemented the logic analyzer and the pattern generator. We used, for plotting, we used pulse view. For signal acquisition, we used libIO and libsigrok. And for decoding, we use libsigrok and libsigrok decode. And it handles a lot of protocols, which like I2C, SPI, UART. And so, for example, here in the screenshot, you can see that we have a I2C signal, and we decode it using the I2C decoders on the fly. And all of this is done with libsigrok decode. Also, there's the Scopy scripting environment. So Qt provides a JavaScript shell that allows the application to be scripted using JavaScript. We implemented an API to set and run the instruments, to use measurements, to use raw values from buffers to analyze them. And we actually use this scripting environment in our factory to do automated tests for the boards. However, there's a downside to this. Scopy still has to run in order to automate the instruments, so that's not as good. When we created Scopy, we had like a modular approach in mind. So developers can create their own instruments. There is the tool launcher class, which provides the container for all of the instruments. The tool class provides a base for all of the instruments, and the I/O context is provided by Scopy. And there's an example if you're into, hacking or that kind of thing. There's an example on our repository on how to do a dummy instrument. We also created, so like I said in the previous slide, that a downside of the Scopy scripting environment is that you need Scopy to run. We created libm2k, which libm2k is a C++ library which makes interfacing with the M2K easier. You don't have to run Scopy. It's just a C++ library. You write your program, you link against it, and you don't need anything else to interface with the M2K. We also created Python bindings for it, and there's a small example there on how to read the analog voltage from the ADC. As you can see, it's just like 6 lines of code. It's super easy. So in conclusion, what we liked about GNU Radio was that we could easily modify the signal chain, modify the signal acquisition. It took very few lines of code. We only needed to change very few lines of code in order to change like major features in the instrument. And the GNU Radio provides lots of blocks that can be used right out of the box, and you don't have to care about the implementation details. What we didn't like about GNU Radio was that there was no easy way to do flow reconfiguration, and we kind of needed that in order to multiplex the instruments. And it was not that good for trigger operation, and especially for single-shot acquisitions. But for streaming, it worked very well for us. So in the future, we also intend on adding support to multiple I/O devices, such as the Pluto SDR. And we want to add better plugin support, so you don't need to recompile everything. Just make use of the JavaScript, or maybe just make your own DLL, but you don't need to recompile Scopy altogether to have your instrument inside our application. Thanks.
5-6 minutes questions.
What are the differences between the Pluto and the Adalm 2K?
So
it's just the connector?
Sorry?
It is just the connectivity?
So the Adalm 2000 is a baseband device. You just use it to do analog measurements without I&Q. There's no LO on it. It's not radio. It's just analog measurements. And yeah, there's, on the analog side of things, you have multiple options, but there's also the digital front end. Does that answer your question?
Yes. And for the price, is it about the same?
Yeah, it's also $100, yeah.
You said you were sampling at 100 megasample per second? And
100
so
megasamples.
Can you stream
No.
all of the samples?
No, we can't stream all of the samples at 100 megasamples per second. We do buffered acquisition. We get data at 100 megasamples per second, and because we have Linux running, I mean, we have the capability to get like a lot of data, but we can't stream data at 100 megasamples per second. But that's also because of the USB connectivity. USB can't handle that amount of throughput.
What about the PGA part? Do you have a space to program your own code? Is something similar to Pluto SDR?
Yeah.
It's identical. So you have two DMAs, I guess, no, to transfer and to receive.
Yeah.
Also, the rest is empty space to your own code. The PGA also have two DMAs, have interpolation, decimation.
Yeah.
Also.
Yeah. I mean, it's a little different because the chip is different, but it's basically the same principle.
It's not the same chip?
It's not the same chip. So we use the AD9963 chip, which is kind of an instrumentation chip. But for the Pluto, we use the AD9363, which is an SDR.
No, but I guess the FPGA is the same FPGA. It's
the same FPGA.
Okay. Okay.
Thank you for the presentation. One question about the hardware. When you do single-shot acquisitions, what's the buffer size? How many samples can you measure?
It's quite big. It's kind of so for Scopy, yeah. For Scopy, yeah, it's 8,000 samples, but with libm2k, you can go way past that. It's just that you won't use this UI, but you can go way past that. I think it's in the tens of 1 million samples.